Welcome to AI Modeling, Inferencing, and Deployment Options, a webinar presented by the SNIA Data Storage and Networking Forum. My name's Erik Smith, and I'll be acting as your host and moderator today, as Tim was unable to join us at the last minute due to a scheduling issue. So as your host and moderator, I'm pleased to introduce you to our expert speakers. First is Luis Freeman, who is a technical project manager covering technology and strategy for storage devices at IBM. And joining him is Kevin Marks, who is an AI technologist and distinguished engineer at Dell Technologies. Before we get into the content, I wanted to provide a quick overview of the SNIA community. SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. SNIA is comprised of 200 industry-leading organizations, 2,000 active contributing members, and 50,000 participating IT end users and technologists worldwide. The SNIA Data Storage and Networking Community, also known as the DSN community, is an active group within SNIA that provides vendor-neutral education and insights for applying network storage standards and associated technologies to a broad spectrum of end-to-end solutions. Now, some logistics for today. The slides for this session are available under the attachment tab at the bottom of your console. Now, if you want to ask a question during the presentation, you can do so by selecting the Ask a Question option and entering your question there. All questions asked during the webinar will be answered either live, if we have time, it's not looking good for this session, or as a part of a question and answer blog post that we try to post no more than 2 weeks after the webinar. Please take the time to rate the session and ideally leave a comment, even if you need to leave early for some reason. We take your feedback very seriously because we greatly value your time and we want to make sure that you are getting the most out of each session as possible. Now, if you want to interact with the people like presenters of this session and other industry professionals, consider joining SNIA in the DSN community. We meet every week on Thursdays at 11 a.m. Eastern. I also wanted to call your attention to the SNIA legal notice. This provides SNIA's copyright notice regarding the use of material. SNIA is not providing any legal advice and there are no warranties expressed or implied. So if you want to reference this material, please do so at your own risk. Before we get started with the actual content, I wanted to just mention that this session is a part of the AI Stack webinar series. It's a comprehensive webinar program designed to demystify artificial intelligence from its foundational concepts to real-world applications. This series is crafted for individuals who are new to AI and aims to build a strong practical understanding of the entire AI technology stack. Those with more practical AI experience can selectively attend webinars, skipping ones that cover familiar ground and focusing on sessions that provide additional insights or education. So why attend this series? Well, AI is rapidly transforming industries, workflows, and daily life, and the field can seem overwhelming due to its technical depth and fast-paced evolution. The AI Stack series addresses this by starting from the basics, building step by step, connecting theory to practice, providing demos, and preparing you for real-world challenges. So today's agenda, first, we're going to have Luis go into deep learning models. Then we'll have Kevin talk about AI model inferencing, AI model serving, and then LLM model basics. And then finally, again, if we have time, we'll have Q&A. But there's a lot of information for us to go over. So with that, I'll turn it over to Luis. Thank you.
Thank you, Erik. Can you guys hear me?
Sound great.
Perfect. All right. On the previous webinar, we explained the relationship between artificial intelligence, machine learning, and deep learning. In this webinar, we will expand into deep learning models and the relationship to large language models. During this presentation, you will hear me say neural networks and models interchangeably. Just keep in mind both mean the same for the purpose of this presentation. Okay, let's move into the next slide. So we're going to talk about what deep learning models are. Deep learning models are multi-layer neural networks that consist of an input layer, multiple hidden layers, and an output layer. The multiple hidden layers are what define deep in the deep learning name. These hidden layers learn patterns on the data and store them as parameters like weights and biases on each neuron. Each neuron is represented in this diagram by a circle. The diagram shows a generic representation of a deep learning model. The number of input and output neurons can vary depending on the model needs. Architectural changes to the design and number of hidden layers is what makes different types of deep learning models. Some examples of these design changes are feedback loops, convolutional filters, and pooling layers. We will discuss the different types in the next slide. There are two main types of deep learning models. If you refer to the left-hand side of the chart, the most recent type of models are called generative models. These are also known as Gen AI for short. This model can create original content in the form of text, image, video, audio, and even programming code. A key distinction of generative models is that they can learn by themselves. They achieve this unsupervised learning characteristic by having two neural networks either working together or in opposition. For instance, generative adversarial networks, known as GAN, achieve this by having two neural networks working in opposition. The generator, which generates the content, and the discriminator, which evaluates the accuracy and quality of the generated data. This adversarial algorithm encourages the model to generate increasingly higher quality outputs. But perhaps the most important generative AI model, with no doubt, is the transformer. This model is the basis for all recent AI advancements and is in use on all modern AI models that spark with the introduction of ChatGPT. We will discuss the importance of the transformer model architecture in the next slide. But for now, let's talk about the other type of deep learning models. The second type of models, as shown on the right-hand side of the chart, are non-generative models. These are earlier models which focus only on analyzing and understanding data and then providing an output. These early models require labeled data for training and learning. A few examples of them are, for instance, convolutional neural networks, known as CNNs, which excel at pattern recognition thanks to the use of convolutional filters on the hidden layer. They are used mostly for computer vision tasks. Another example are the recurrent neural networks, which incorporate feedback loops on the hidden layers and allow for the information to persist across time steps. And these ones are mostly used for natural language processing and time series forecasting. Let's move over to the next slide and talk about the importance of the transformer model architecture. The transformer model was introduced in 2017 on a paper titled "Attention is All You Need." This architecture overcame the limitations that previous natural language processing models, like recurrent neural networks, had with regards to context. Previous models could not differentiate context. As an example, we'll group together bark, as in dog barking, and bark, as in tree bark. The self-attention ability of the architecture allowed the model to calculate relationships and dependencies between words, especially the ones that are distant to each other. The second characteristic of transformers is that they allowed to train huge amounts of data in parallel, allowing the recent advances in AI. As of today, transformers have been successful both on natural language processing and computer vision fields. Initial deployments of transformers were on large language models and were only focused on understanding and generating text. Most recently, transformers have also integrated computer vision using vision transformers to create feature vectors that in turn are converted into word embeddings. This is allowing for vision language models that allow multimodal input using text and visual data like images or videos. By now, you should be able to understand the relationship between LLMs and artificial intelligence. In a nutshell, LLMs and VLMs are models using the transformer model architecture which is part of the generative AI deep learning models. We will now switch to the next item on the agenda and talk about AI model inference. But before we do that, we need to talk about what the life cycle of machine learning is. The cycle starts on the left-hand side of the chart with the training of a model from scratch using a data set. The model learns from that data set by recording and adjusting parameters like weights and biases on each neuron as the data set is ingested. The next step then becomes the fine-tuning of such pre-trained model to adapt it to a specific task. On the third step, the pre-trained model is then tested during the inference cycle to verify that the model can make accurate predictions. Think of the inference stage as the final exam for a student after learning a course. Then the last step on the cycle is serving the model. It is also known as deploying the model into production. Note that the cycle repeats for continuous improvement using practices called LLM operations or machine learning operations. Note also the comparison in terms of resources needed to train a large language model versus a CNN. This is the main reason why non-generative models, which are one of the first ones that came out, continue to be in use today, because the small size of these models allows for deployment in situations where resources are limited. In this webinar, we will focus on learning about inference and serving. The demo will be specifically tailored to inference of LLMs, which are based on generative AI deep learning models. Future webinars will focus on the training and fine-tuning stages. All right, so let's start now talking about inference. So what is inference? Inference is the process where a pre-trained model uses its learned knowledge to analyze input data and then come out with a prediction. This specific diagram explains inference for a computer vision example. Starting on the left-hand side of the chart, inference begins with new, never seen before data. In this case, a new picture of a cat. The image must be processed to fit the input layer size of the pre-trained model. In this example, the model architecture uses black and white 32 by 32 pixel images for a total of 1024 pixels or inputs into the model. The image must be converted accordingly on a step called encoding. Note that each input neuron is capturing the hue of gray for each pixel on a value between 0 and 1. The pre-trained model processes the input data in the same way it was used to train the model, but without altering any parameters like the weights and biases on the neural network. Processing the data is called doing a forward pass, because the data flows forward, entering via the input layer and through the hidden layers of the neural network, activating specific paths and neurons, and producing a prediction or classification on the output layer. The diagram of the neural network shows highlighted in shades of gray how different neurons and neuron connections are activated, resulting on the output neuron that represents the cat having the highest activation, as shown on the dark, almost black gray color of the neuron. You can also see other output neurons being activated, but to a lower extent, as shown with the light gray colors, shown on the dog and camel neurons. This then translates to the probability scores for each one of the neurons. In this case, 93% for the cat, 24% for the dog, and so on. The highest probability score, in this case the cat, is selected as the output. Note how inference for computer vision only requires a single forward pass on the neuron network. Let's now do the same for inference on LLMs. Inference on large language models begins with the user entering a new prompt. In this case, the first 4 words of the popular joke, why did the chicken cross the road? The prompt is then broken down into tokens on an operation known as tokenization. The token IDs corresponding to the first 4 words, why did the chicken, are pre-filled to the input layer. The pre-trained model processes the pre-filled data, doing a forward pass, activating different hidden neurons and connections, and coming out with predictions, known or tokens, and their corresponding probabilities. Tokens are ranked and decoded to their corresponding word. The highest ranking token, in this case, cross, is selected as the output. The token ID for the selected word cross, in this case 0257, is appended to the previous prefill, and another forward pass is performed, resulting on a new token prediction on the output. The cycle continues with each new output token until the new model outputs an end of sequence token. This characteristic is defined as autoregression. Autoregression makes inference costly because the prediction of each new token depends on the computation of all previous tokens. In the next slide, we will discuss in more detail the challenges and solutions to optimize inference. As I mentioned earlier, the autoregressive properties of transformer models, and therefore of large language models, make inference slow, as it generates one output token at a time. This also makes inference very costly, as each pass forward requires loading all the model parameters into the AI accelerator memory for compute. We are talking about billions of parameters, which equate to hundreds of gigabytes of data being moved and processed with each pass. It is important to note that the bottleneck is memory bandwidth to transfer the data, and not necessarily compute power on the AI accelerator. To overcome the inference challenges, AI engineers work on optimization techniques. Kevin will be explaining batching, caching, and parallelism techniques during the demo. Therefore, I will only briefly explain model size and architectural optimizations. Optimizing the model size is done by a technique called quantization, which basically reduces the resolution of the parameters from 16 bits to a lower number, for example, 8 bits in this example. This, by reducing to 8 bits, basically cuts in half the amount of data that needs to be moved over to the AI accelerator at the expense of some loss on accuracy on the output. There have been cases that they have been successful even going to a quantization of 4 or even 2 bits. Architectural optimizations, like speculative decoding, use a small quantized draft model to guess the next, say, 4 tokens on the output. And then all 4 are validated in one pass using the standard size model, which is known as the target model. The logic is simple. If the probability score assigned to the draft token is equal or higher to the probability from the target token, then the token is validated. Otherwise, the token that failed validation, as well as subsequent ones, are discarded and replaced by the tokens that were generated by the target model. In most cases, this results in processing 4 to 5 tokens at a time with each pass of the target model. Last, I want to mention that there are inference frameworks like VLLM, TensorRT LLM, and others that help with these optimization tasks. Kevin will be using VLLM during his demo. We're going to now move to the next item on the agenda, which is AI model serving, which is also known as model deployment into production. Model deployment makes the model available to the end user. Depending on the use case, the end user can be a software application, like for example, Microsoft Copilot. It can be an AI system, like a self-driving car. It can be a software developer, or even you or me over the internet asking questions to a web application like ChatGPT or Gemini. Depending on the use cases, the model can be deployed in one of two ways. The first type of deployment is shown on the left-hand side of the screen. It is on the cloud or on-premise. In this deployment, the inference runs on a powerful system in data centers. This deployment type is ideal for applications that require scalability and massive inference power for complex models. Inference can be run in one of two modes: in real time, which is known as online inference. And an example of this type of inference is, for instance, web applications like ChatGPT. And in batch, which is known as offline inference, where the information is collected and then processed at once. An example of batch processing will be collecting stock market data during the day to then process it overnight for insights. The second type of deployment is shown on the right-hand side and is called on the edge. Edge deployment is used for applications that require instantaneous response, where latency across networks or the lack of internet connectivity is an issue. Another use of edge deployments is where data privacy is a concern. In this type of deployment, inference runs on dedicated devices that are part of the actual solution. Examples of edge deployments are self-driving cars and drones, where immediate response is critical. On the next slide, we will talk about the challenges for LLM deployment. Now, deployment has several challenges, and we could probably spend a full session talking about that. In the interest of time, I will leave you with a few bullets for you to read at your leisure. Note that this list is not comprehensive of all the challenges. I'll move next to the last of my slides. And I just want to mention that there is a set of practices and tools that are used to manage the entire life cycle of LLMs. This includes both inference and model deployment. This set of practices are called Large Language Model Operations, or LLMOps for short. LLMOps basically leverage the same principles of machine learning operations, but adds additional practices for prompt engineering, for example. In the interest of time, I won't go in detail, but this chart shows you the practices and some of the tools that can be used. This completes my presentation, and with this, I will transfer over to Kevin, who is going to take us through a demo and some inference optimization techniques. Kevin, the floor is all yours.
Sorry, I was trying to find the mic.
No worries.
What's up? So, to start, I'm kind of dealing with a head cold and a cough. So if I go on mute, it's because I'm probably coughing. So my plan is to kind of cover a couple topics in terms of the inferencing process that in a little bit more detail than Luis talked about. Talk about different parallelism, different types of parallelism that's used, and then do a little bit and end with prefix caching. And with all three of those sections, kind of do a demo of each. I will not be covering some of the topics like quantization, speculative decode, MOE parallelization, or some of the KV cache tiering and disaggregated inferencing that's kind of hot in the industry right now. We may plan on doing a follow-up seminar on those topics. So as we look at the inferencing process, it generally contains two stages. The prefill stage and the decode stage. The first stage is the prefill stage, as Luis described, and this is where the model essentially gets the entire sequence and then chunks it at the subunits and then tokenizes it and maps it to a vector space so that the model can understand. In the context of what I'm showing on the screen is tomato or fruit is the input and the context going into model. But it doesn't have to be just a prompt. In terms of, let's say I uploaded a file and said, hey, can you summarize this file? All of that is context going into the model. So after it does the prefill stage, then it generates the first token. And that's kind of where the prefill stage ends from an application perspective, because that's the first token that you get back. And then it auto-regressively, as Luis explained, generates the next token, the next token, the next token, until it gets this concept to meet a criteria to stop, whether that's max tokens is hit, like I will use in my demos, versus hitting a stop where it's decided that it's essentially answered the prompt and is no longer going to generate any more tokens. So now if we look a little bit deeper into the transformer and the concept of KV cache, right? So every time you generate a new token, right, you have, let me put my little pointer on so you guys can see it. The transformer model is built up in these kind of layers, and these inside here kind of represent the hidden layers that Luis talked about. And for each token, you essentially end up with three vectors: the K vector, the V vector, and the Q vector. I wasn't really going to talk about them in terms of the math that's involved, but I wanted to highlight that the K vector and the V vector are always needed for future tokens. And so the concept of KV cache is to essentially build that up so you can reuse them with each next token that you're generating. Right. And so it's kind of a process to speed up the inferencing process. So, and what this really does, it avoids the recalculation of all the previous tokens that you're adding as you generate output. And this is very obviously, looking at the screen, very computationally involved. So now if we go back to the picture, we now have this concept of KV cache, and this is obviously you build the KV cache for the prefill, and then as each token gets generated, this KV cache grows and grows and grows, and assuming there's KV cache memory available. And this, as it grows, as the KV cache grows, it's persisted to the end of the sequence. So basically anything from the start of prefill all the way to the last EOS token is all maintained until the sequence is over. Now, in the future, we're talking about KV cache, like storing the KV cache for future use, and we'll talk a little bit about that after. But without the enablement of what they call prefix caching, it's all kind of thrown away at the end. So now I kind of wanted to define some terms that are kind of used in the industry. Concepts like time to first token, and that's essentially the time from when you issued your prompt to the inferencing server to you get the first token. So that's kind of tells you how fast the system is doing prefill. And then you have the concept of intertoken latency, and that's essentially how long does it take from one token to generate the next token. So you have an intertoken latency from here to here, from here to here. And then lastly, you have the concept of the prompt time, or the end-to-end latency, and that is from the start of when you issue the prompt all the way to when you basically finish the prompt. The other thing I kind of wanted to mention here is that the prefill phase, because everything is known as the input, so the whole input context is known, this can actually and is done in parallel. So it's kind of a parallel operation to generate the KV cache for this, versus in the decode phase, because it's iteratively, it's all done sequentially. So you'll notice, and I'll do a demo that shows you kind of the difference in performance between prefill and decode. Now the prefill, because it's very because you're doing it in parallel, is very computationally involved. Because it's parallel, you end up, in a lot of cases, being compute bound here. Versus the decode phase is very memory bound, because you have to load all the weights, you have to load all the KV cache, you have to do the dot product, and so so you end up being memory bound in generating new tokens. Now, when we talk about compute bound and memory bound, this is only what I call one sequence. Now, you can think in reality in an online inferencing environment, there's many of these going on concurrently, and they're kind of at different phases of the of their process. Some may be starting prefill, some may be starting decode, some may be halfway through prefill, and there's lots of controls or in most of the inferencing servers that kind of control the balance between prefill and decode of what I'll call the batch, or what the active working set is. So the other thing I kind of wanted to point out in this graph is that the TTF actually is, if you look at TTF in terms of the input sequence length, so here's a graph showing the input sequence length from 0 to 1,000,000 tokens. And as you can see, the TTF, so this is kind of only generating one output, or excuse me, one token output. The TTF is quadratic in nature, versus this line is a linear line where I basically grab the slope at probably 10,000 token and 20,000 token, grab the slope and grab it. But the point is really to highlight that as your input context grows, TTF is a quadratic, and it's not a linear function. Okay. So I have this demo environment, and what I'm actually using VLLM. I could have easily used SGLang or TensorRT. I just chose VLM because I already had it set on the system I'm using. And what I'm running is a model on an H100. No parallelism techniques going on. It's just the model running on an instance. And the other thing I wanted to point out down here is for my parameters for my tool that I use, ISL stands for input sequence length, which is really the length of the input prompt. OSL is the kind of maximum number of tokens that I said it can return. And then NP stands for number of prompts, which is the concurrency, which is kind of the number of prompts that I'm running in parallel. So now I'm going to jump to my demo. Hopefully everyone can see it. So starting off, this is a script or a tool that I wrote that I use. I could have easily used some of the industry tools like GenPerf AI, AIPerf, or any of the benchmarking tools that come with the different inference servers. I use this one because it allows me to kind of experiment with different things, and I can show a lot of debug output. And so that's why I'm kind of using it here. And as you can see, this is the host, that's the port. This is the model I'm running. So it's a DeepSeek R1 distilled version of Quinn 14. And I'm using what's called the OpenAI chat interface. So that's kind of OpenAI API is kind of the de facto standard for inferencing right now. So that's kind of what I'm using it. And then this is my prompt, and this is my output sequence length. And so what I wanted to kind of show you, and this is in debug mode, so you'll see a lot of stuff up here. But kind of what I wanted to show you is that this is essentially a post command, an HTTP post, where I'm giving it kind of the prompt. So this is the role user content is kind of the format for the chat interface. And this is actually the prompt. Here is my max tokens where I'm saying, hey, please don't output more than 100 tokens. And then because this tool is used for a lot of benchmarking, I also set a min token, which is kind of to tell the model, hey, please output a minimum of 100 tokens. And so you can see that the max and min are sit together so that it, in general, will normally output 100 tokens. Even if it has nothing relevant to say, a lot of cases it'll output a bunch of junk after it. Now, even though I'm outputting junk, it still goes through the auto-recipe process. So it doesn't affect performance anymore. And then I set the temperature, which controls some of the sampling parameters around the probabilities that Louise talked about on the output about which ones it can select. But I hadn't planned on covering that anyway. And then lastly, in this case, I set stream to false. And that basically means that give me the whole answer in a single output. And so this is an output structure for OpenAI. You can see the answer right here, which which the model generated, and then kind of token information about how big the prompt was, how many total tokens it generates, and output tokens. And so the next command, what I'm basically doing is enabling streaming. So now this stream becomes true. And I just wanted to show you kind of the output structure in that case. So now if we go back and look, the stream is true. And then I also included another parameter called include usage, which essentially provides me with this output structure to tell me how many tokens I used, how many tokens were in the input, how many tokens were in the output. But now as you look at the streaming response, you see a bunch of data packets. And essentially each data packet contains a token of the answer. And if you look right here, you'll see it'll match kind of above. Okay, so I'm trying to figure out, right? So, and this is kind of what allows you in a chatbot to show where you see it like streaming across the stream, is because it's returning every time the model generates a new token, it sends it on. So now we're going to change a little bit, and I'm no longer going to use this. It's a tomato, a fruit, and I'm now using synthetic prompts that my program has generated up to the number of tokens that I'm requesting. So now we get into the ISL and the OSL, right? And so the ISL is the input sequence length, and the OSL is the output sequence length. And the reason I wanted to show this is that I wanted to show you the difference in performance between prefill and decode. And in this case, I enabled this argument right here, which essentially allows me to print the kind of performance of every prompt. But in this case, there's only one prompt, but it still works. And so now if you look at the prefill token rate, it is around 10,000. But the decode token rate is only around 85. So this is kind of the parallel of prefill versus the sequential of the decode output. So there's quite a, what is that, like 100 and, I can't even do math right now with my head, but it's quite significant orders of magnitude difference in response. So now what we're going to do is in the next command, we're going to kind of ramp the input sequence lengths from 10 to 100 to 1,000, 10,000, and 1,000,000, and kind of see what happens to the performance numbers we're seeing right here. And as you can see, and I didn't explain above, right? The tool actually outputs the reported number of input tokens that it got, the output tokens, kind of the total token rate. So that is the input plus output divided by time, which gives you the total token rate, and then just the output token rate, which is essentially from when I got TTF to the end divided by the number of output tokens it generates. So that's kind of what you see. And then you'll see the average prompt time, the time to first token, and then the inner token latency, the average of each token that got generated. What was the difference between each token? So now we'll let this run. And as you can see, the TTF starts to grow now, right? You see it growing, and the other one's kind of still running. And if you were to plot this TTF right here, you would actually see that it is quadratic. It is actually quadratic in nature. And you may be wondering why these input reporteds are different from kind of the ISLs that I ask. And part of the reason for that is that the chat interface adds a bunch of tokens depending on what you call the chat template it is. And secondly, I'm running these commands with this thing called CD, and for me that's called the cache defeater. And so it's actually putting part of a UUID in front of the prompt, and it is essentially to prevent prompt caching. And we'll talk about that a little later. So that's why these input values are a little bigger than what I actually requested. So now what we're going to do in the next command is we're going to hold the input constant, and we're going to grow the output. And so if we look at that, and the one thing I didn't mention is all of these are what I'll call a concurrency, or a number of prompts of 1. So now if we look at this, we'll notice that the TTF should be almost identical, and it's pretty close. Sometimes when the system is idle, you get a longer TTF on the first one, and this is because I'm not running with a warm up to speed up the output. If I were to run with a warm up, then these would be identical. But what I wanted to highlight in this is notice that the ITL, whether it's 10, 100, or 500, is pretty much the same because it's an unloaded system with one prompt. And so the process of generating the next output token is almost linear. It's not always true, but almost linear. And then lastly, the last one I'm running for this part of the demo is I'm holding the input constant. So the ISL, I'm holding the OS head constant, and now I'm applying concurrency to it, which means all of these, like 1 prompt and then 10 prompt, 100 prompt, 250 prompts, all get basically issued at the same time. And so they're all getting fired off asynchronously. And so if you look at this now, you can notice the prompt time grows, the ISL starts to grow, and the TTF and the TTF grows, and then the ITL grows as this thing gets loaded. But you notice that the original, we started at 81, and now we're up to like almost 4K. And that's because of we basically parallelized the decode of the different streams. All right, so now I'm going to actually let this run and go back to my presentation. Hopefully is somewhere there. All right, so now let me talk about the anatomy of an inferencing server. And this is kind of at a high level. This is obviously VLLM. And you kind of have different inputs. You can have a gRPC input, which is used for kind of offline batch, and it's also used for when the AI application process is in the same machine as the VLLM instance. Now, all of my work is going through HTTP and using this OpenAI inferencing server, and then it gets into the async engine, which we'll talk about in a minute. So the basis of like the model all runs in the LLM engine. So you have the input processing, and this is really about tokenizing your inputs. You have a scheduling, which is scheduling which requests are getting processed into the batch. So how things that came in from the HTTP server asynchronously get merged into kind of the working set of what the model is working on. And then, and additionally, with the model execution, kind of how the steps to process both decode and prefill are worked into what the GPUs are actually executing, right? So like I said prior, the batch concept is you could have sequences that are in prefill, some in decode, and essentially the combination of the scheduler and the model execution unit is determining what parts to work on for what parts of the sequence. And then lastly, you have the output processing, which is essentially, I got my output, as Louise said, oh, it's token number 774, convert that back into a human readable text. And then it's this guy that actually sends it back. If you're doing streaming, it sends it back one token at a time back to the application that did the call. And the other thing I wanted to mention is, in general, for like most inferencing servers, they support chat completions, and they support text completions, and they support metrics. So you can connect Prometheus to it and look at a whole bunch of metrics around TTF, around KV cache usage. Lots of them are in there that you can take a look at. So now I kind of wanted to talk a little bit about what I'll call typical graph shapes, and this is relative to concurrency. So these lines will all move with different inputs and outputs, but these are kind of general graphs around tokens and concurrencies, right? So, and what you'll notice here is that as the concurrency ramps up, the output tokens or total tokens ramps up and then kind of flatlines. And this is where the system becomes memory bound and really cannot do any more work. From a time to first token perspective, you have a similar thing, but now you're getting compute bound. It can't do prefill any faster, and therefore, as more work comes in, the TTF starts to grow because because it can't do any more work. Inter-token latency is kind of similar and related, but it has a little different graph sometimes. And you may be wondering kind of why the ITL kind of starts to flatline here. And that's generally because it can't do any more work. But you have to remember that inter-token latency only starts in terms of when you start looking at from one token to the next till after TTF. So if I have prompts that are like sitting there waiting that haven't even started to work, even though I as an application client have issued them, right? TTF will continue to grow because I've issued it and I'm waiting for my first token. But that generally does not affect the inter-token latency, right? Because the inter-token latency only starts when since I've got the first token. And then prompt latency is kind of similar because it's essentially related to both the time to first token plus this rate, right? So if you look at prompt latency, it's the time to first token and then times this inter-token latency, or should I say plus the inter-token latency times the number of output tokens generally equals the prompt latency. Okay. So now we're going to talk a little bit about data parallelization techniques and kind of when you would use them and why you would use them. So the most basic data parallelization technique is essentially run multiple copies of the model, right? Now you can only do this if the model actually fits inside the single GPU, right? And essentially, so you run a full copy here, full copy here, full copy here, and you have this kind of load balancer that fires the prompts off to these ones. Now in this case, the model weights are loaded on every single one. And so you only have so much memory left over to do for KV cache, or what I'll call the working set of the prompts you're processing gets reduced because you have the model weights loaded in every single one. But there are cases where this excels over other model parallelisms. Next, we have tensor parallelism. And this is essentially, if we looked at that model way back on my second slide, where you had all the layers, you're going to split the models vertically and give half of it to one model and half of it to the other model. And this is used primarily when the model does not fit on the GPU. Or there's another case where you're actually looking for lower latency at lower concurrencies. And we'll kind of demo this in a second. Generally, this can be run what I'll call multi-node. So you can actually split the model across two different nodes, not only GPUs, but nodes. And that is done sometimes. But the other, what I'll call more preferable way to do it is called model parallelism. And this is where when you look back at that slide where you have the different layers, what we're going to do is, instead of breaking it vertically, we're going to break it horizontally and run different layers or different sets of layers on a different GPU. And so for every token as it goes through the layer, assuming that it's a 4-layer model, it has to flow through each one of these as it flows through the hidden layers to get to the output. Now, the downside of pipeline parallelism is that you kind of created essentially a pipeline. And so there are cases where, especially with low concurrencies, that you have pipeline stalls because there's no work to be done. There's no work to be done by these lower layers. And so that's why in a lot of cases, they have these concepts of micro batches where you batch a bunch of work together and then send it through to keep all the different layers busy at times. And the pipeline parallelism is normally applied where you have kind of a lower bandwidth interconnect between the different GPUs versus tensor parallelism is normally when you have a higher amount of GPUs, such as if you have NVLink in between them to basically communicate all the collectives you need, such as all reduce or all gather, between the GPUs in order to generate that output token. So, why are my slides? So now I'm going to have like a more expanded demo environment. And in this demo environment, I have the original one that I ran on my first in my first demo, I have one that's running tensor parallelism. So they have the models split across two GPUs. And then I have an instance where I'm doing data parallelism, where I have two models running the model. And I'm actually using the one from over here as the second one. And I have a load balancer on top. And lastly, actually this morning, I added this one to show you kind of pipeline parallelism, where I redrew it this way to kind of indicate that half of the model layers are running on the first GPU and half the models are running on the second GPU. And if you actually watched it execute, you could actually see it, especially at the low ones where it would use the first GPU and then the GPU. But in any case, so now what we're going to do is look at the data look at that. So I started this before I jumped back. So if we look at the data output, we're going to focus on these four. So here we have no parallelism, and you can see I ran a 7,000 in and a 100 out at a bunch of different concurrencies, and you can see the values I got. And then this is tensor parallelism, so I'm using two GPUs. This one is data parallelism, so I have two copies of the model running. And lastly, I have pipeline parallelism, which means I have the model running the model's running across two GPUs in a pipeline fashion. And a couple of things that you'll notice here, and which you would expect, right? So when the concurrency is 1, I get about 62, and this is on no parallelism, I get about 62 tokens per second. And in data parallelism, when the concurrency is 1, I also get about the same answer. And this actually makes sense because it load balances across the two models. And when there's only one prompt outstanding, you're essentially only talking to one. And that's why these should be identical. And as you can see, they're pretty close. And now as we ramp up, you can see that in the single case, how it knees off, right? So at a number of concurrencies at 50, I'm at 221, and at a concurrences of 100, you can actually see it slow down, right? So versus, and then if we look at tensor parallelism, it continues to grow, and you can see it's kind of just hit its knee. At 100 concurrencies, it just hit its knee. Versus data parallelism, and this is where I'm actually talking to two models. You can see it also just hit its hit its knee, but the performance is a little better. And so if you look at like all the different parameters up here, you can see that obviously this one's going to be the worst because it's got less GPU power, right? This is only one GPU versus these two are two GPUs. Actually, all three of these are three GPUs. But what I kind of wanted to highlight that in some cases, especially when the input is bigger than the output, it actually performs better in most cases with running two copies of the model. And you should be able to see that. You'll see that like the TTF here, they're about even. And then as it goes higher, you'll see that the data parallelism one actually ends up doing better than tensor parallelism. And I don't really advise that you run tensor parallelism, especially at numbers greater than 2 for small models, because it actually becomes ineffective. And then lastly, I added pipeline parallelism, and I wanted to kind of show you that in this case where I do have NB-link between all my GPUs, that it actually doesn't do as good as the pipeline or as the tensor parallelism. And one other thing I want to show you. So these are my if it clicks over, here. These are essentially all my models running, and I just wanted to show you that in VLLM, you can see that these two are running in tensor parallelism. That's what the TP0 and TP1. So those are the two ranks of the tensor parallelism. And down here are the two pipeline parallelism ranks. And if I were to run, you would see these actually shoot up and use the GPUs. And this is just a program called NVITop. That is, if you use NVIDIA GPUs, very useful. And then lastly, we're going to let this run. And this one, and I can show it to you running right here. So this is obviously using the two GPUs that are running in pipeline parallel. Excuse me, tensor parallel. Let me go back. Really struggling with. Okay. So I ended up graphing the results that of the ones that I just ran, so you guys can look at them later. But the kind of thing I want to show you between pipeline parallelism and tensor parallelism, you can see that as the load increases, this blue one actually comes up and matches the tensor one pretty close. And that's because it has enough work that the pipeline doesn't stall anymore. But you can see down here, you're having stalls in the pipeline relative to tensor parallelism. And I included all the graphs just for you to go look on after, later if you like. And then here's kind of some examples of TP1, TP2, TP4. And again, this is a small model. These are not actually the model I'm running. These were old graphs, but I just grabbed them for the sake of the slide. But you can see that you don't get linear scale as you add more GPUs in tensor parallelism with small models, right? So this is TP1, TP2, TP4, and TP8. And this is only a single input size where I'm increasing the concurrency down here. And then for each of these output sections, I change the output token rates. Now, it was a poor choice on my part for actually graphing total tokens instead of output tokens. But you can see that at this point, like here, that TP4 and TP2 are almost giving you the same data. And then my next slide really compared, saying I have 8 GPUs. Here's the different configs that I can run it in. TP8, 2 times TP4, 4 times TP2, and 4 times TP8. And the one thing that I forgot to mention back on the parallelism slide is that in many cases you can actually layer these different techniques on top of each other, and that's kind of what you're seeing here. This is basically data parallelism of 2 and tensor parallelism as 4, and you lay them on top of each other. Now, in a lot of these graphs, you'll see this thing shoot up, and this is because I have not given it enough load for it to basically knee, and you would expect it to kind of knee over if I increase the concurrency, and so I really haven't done that. And so I would actually normally, if I were looking at performance on this stuff, I would go back and rerun these with a longer concurrency to find out kind of where the knee is. So let's peek. Okay, and so my last kind of quick section is really on prefix caching. And this is where, instead of getting rid of the KV cache at the end of a sequence, if I have extra memory available that's not being used for sequences, why don't I keep it? And then I can reuse it if the prefix for a next hash or a prefix for another prompt is the same. And so the kind of idea is, a dog that had a bone. Well, a dog that had a bone versus a new request that came in and said a dog has a bone that. So it's that versus which. Now prefix caching generally works on a block basis, not on an actual token or word basis. But to get the idea across, the concept is, well, I could reuse this, and then I wouldn't have to regenerate KV cache for these blocks. And there are certain use cases where this actually makes sense. And so if you think about RAG or conversational history, right? So when you're doing conversations, right, you jump back and forth between, you started with a conversation, and then you ask it another question. Well, when RAG actually when conversational history works, everything above actually gets sent back to the model with your new prompt. And so over time, that all gets repeated and repeated and repeated. So if you had that in your KV cache and you didn't evict it, then you wouldn't have to do prefill on that amount, on that conversation. And so that's kind of what I ran right here as my last demo is. Now the script is different, but it's actually calling the same tool. And what I'm doing is setting the hit rates for the different prompts, and which is basically I set all the prompts to have a commonality of nothing, 30%, 70%, 100%. And you can see that the output token rate going from no cache hits to 100%, more than doubled, while the prompt time came down from 3 seconds down to 1. TTF went from 1 second down to 0.1 seconds, and the ITL also dropped because the reason the ITL drops is because I'm not having to do pre-fill work, so I can dedicate all the time into doing decode work. And so my last slide here is really just kind of that graph, an example of that graph showing the TTF coming down and the pre-fill going up. And so my last slide, kind of the end, is to really say that this is kind of the inferencing stack that we're looking at, currently and in the future. And this is the part I kind of demoed and talked about today. There is so much work going on in terms of building an AI inferencing structure that can reuse KV cache, that can offload it to storage using things like Nixle, like Mooncake, with KV cache managers from LM Cache, Dynamo and Mooncake. So kind of the highlight of the point is really what I covered today is just this little part.
Thanks, Kevin. So we don't have any time for questions. We're actually out of time. So we'll just move to the next closing slide. Please rate us and provide us with your feedback. This webinar and copy of the slides are available at the SNIA Educational Library. A Q&A from this webinar, it'll be a blog, will be available at sniablog.org. And then please follow us on LinkedIn and on X. And thank you very much for your time. We really appreciate it. Thank you.